But I know Amara needs to go to another class after this, so we will get started with her talk now. Today is one of my favorite days as the person that helps put together the Science Speaker Series, because it's a day when we celebrate you guys and your achievements. And so today we are going to celebrate two students who are graduating with their bachelor's in astronomy this semester, Amara Williams and Nicholas Hernandez. Congratulations to both of you. They will be talking a little bit about their capstone projects and what they've been working on with myself and Dr. Ratchford. But we do like with the student talks to fill more of an hour. So what we're doing today is we are also going to have a bit of presentations from 4 of our own students that went off and did an REU or internship this summer. And that's with Clarissa, Mari, Amanda, and still to arrive, Janessa. So everyone should be able to have a good time. So today, what we have is our presentations are starting with Amara Williams, who's going to tell you some of the work that she has been doing on the eclipsing binary UW Canis Majoris with myself. So Amara, come on up, and you can give your presentation.
Hello? Okay. Hi. So my senior project was on the eclipsing binary of UWCMA, and my name's Amara, and my mentor was Dr. Richardson. So to start off, some just stuff about the CWCMA or UWCMA was that it's an eclipsing binary. Its spectral type is 07, which is hot massive star, and Roman numeral IA, or 1A, and that's the luminosity of a supergiant. And it was first discovered to have spectroscopic variabilities by Frost in his paper in 1906. So to start, this is just an example spectrum. We obtained the spectrum from the telescope in Chile. It's a 1.5 meter telescope with a Chiron spectrograph. This is just an example of one out of 132 sets that we collected. The blue one, or the blue spectrum, is a mostly reduced, and the orange is the final reduced and normalized spectrum. The absorption line for this was helium-2, 5,411 angstroms. And as you can see, this was only just of the primary star. We can't see the secondary star yet. So next, I had to fit a Gaussian for this. The Gaussian gives us information of the primary star motion. The center of the Gaussian represents the radial velocity, and the HJD, or heliocentric date, represents the time. And we did this for each of the spectrum. Next, I had to take the HJD and the center Gaussian and fit it. Here are the results. The left is showing the radial velocities plotted compared to time, and the right is the binary period. And we found that the period was around 4.39 days. So next, we had to we fitted this in Python using Binary Star Finder to obtain an orbit fit, which is the orange line. We saw that this was nearly circular in the plot, and this is still just for the primary star. Next, we started to look at the test data. The test data shows the brightness of the star compared to time. This is over a 1 month period that it observed UWCMA. You can see in the data that there are eclipses, and this is from 2019. Next, I did the 2020 and the 2021. This data for the 2021, there's a bit of a spike in it, and we think that it is from instrumental problems in tests. And so the next steps for this are that we, as you can see, we didn't find the secondary star motion. So in the future, we hope to get more data for that. And using that, we can combine the test data to put into a eclipsing binary software, or Phoebe, and that will be able to find the radius of the primary and secondary and the masses of both stars. And that's it.
Do we have any questions for Amara today about her presentation? Well, great job, Amara. Let's thank her again, and congratulations on your upcoming graduation in just like a week. So, yay. All right. Our next talk today is Nicholas Hernandez. Nick has been with here at Embry-Riddle for a little while, and he's graduating with his bachelor's also in about a week. And he did his capstone research with Dr. Ratchford, studying pulsations of Delta Scuti stars. And so, Nicholas, have fun.
All right. Hello, everybody. I'm Nicholas Hernandez. My topic is on Delta Scuti stars. So what is a Delta Scuti star? It's a variable star that is somewhat larger and hotter than the sun. It is found near the main sequence line, just in the instability strip. The periods range from minutes to hours. Their pulsations are a combination of different modes, examples, spherical, angular, and then the surface variations are caused by processes deeper inside the stellar interior. So the graph on the top, the blue dots represent the Delta Scuti stars. The red lines represent a model where the Scuti should be. So the black line represents where the main sequence is, and then the green lines represent the evolutionary path of stars of different masses. And then the graph on the bottom, the white dashed line represents Delta Scutis based off of observations, and the color shaded regions represent the fraction of stars that are Delta Scutis, with the lighter colors being a higher fraction of Delta Scutis. So the data was taken from tests where observations measure the star's brightness. Observations covered 600 to 1,000 nanometer range, and then the stars show the brightness variability over a period of time, as shown in the graph on the top. The program used to determine the frequencies of the pulsations is the GLS, which stands for Generalized Lomskargel. It's a periodogram commonly used in frequency analysis. You input the star flux and you output a periodogram shown in the bottom graph. So in the results, these stars were chosen because these stars have high frequency pulsations, and also because there is data from ground-based observations. So in this group of stars, most of the stars have frequencies between 40 and 70 cycles per day, where high frequencies tend to be equally spaced. One of the interesting stars in this group is the V star, highlighted with the red arrow. It has 4 strong peaks with 4 sub-peaks that are equally spaced. V star has also been noticed by 2 other groups, KCM and Betting T. The spacings of the 4 strong peaks is about 4 cycles per day. And Betting T noticed that a lot of the high frequency stars tend to have high frequencies that are equally spaced. And then in the bottom left graph is a graph from KCM, which is on the same star, V star. And then that's my presentation, references, and then some extras where the chart on the right are the stars that I observed or taken from tests, and then they're organized by the sector they're in. And then the test picture shows where tests observed for each sector, where the red circle signifies 351 days per 2 years of observation. And that's the end of my talk. Thank you. Any questions?
So how many frequencies did you find on the other stars?
A lot. Okay.
All right. Are there any other questions for Nicholas today? Let's thank him again and congratulate him on his upcoming graduation. That was the 2 capstone presentations we had for today. And now what we're going to do to kind of fill out our science speaker series is we have 4 students that this last summer had opportunities with either research experiences for undergrads or internships that they were going elsewhere to do research. And so our first talk today is going to be Clarissa. And Clarissa Paveo went to the SETI Institute this summer. And she will be talking about her work involving, I believe, meteors or comets or
Meteors,
both.
same thing.
Meteors are just leftover comet stuff.
True. Okay. Hi, everyone. I'm Clarissa, and as Dr. Richardson said, I did my RU at the SETI Institute in Mountain View, California, and SETI stands for Search for Extraterrestrial Intelligence. And I didn't directly look for little green men, but I did use deep learning to investigate the diversity of comets. Let's see if I can use this. Okay. So comets are the most primitive bodies in our solar system. And understanding where these comets come from and their composition can tell us a lot about the early materials and processes that happened in our early solar system. And we can find the origins of the comets in their parent comets, and as well as the composition of these comets. And that can tell us the diversity among different comets. And to be able to do this, that's where the CAMS project comes into place. So CAMS stands for Cameras for All Sky Meteor Surveillance. And funny enough, we have a CAMS box at our school here on top of the observatory, if no one knew that. And CAMS is a bunch of cameras all around the globe, all looking at the night sky every single night in search for meteors. And if more than one location around the world finds a meteor and they see it in their video surveillance, they are able to triangulate it and find the direction and speed. And if you find the direction and speed of a meteor, you can tell the parent comet, and that tells you the origin of this comet. But if you want to know the composition of these comets, that's where CAMS spectrograph comes in. And if I can get the laser pointer, maybe not, right here on this one, is the spectrograph in Sunnyvale, California. I took that picture of the spectrograph, and here is a less weathered picture of the up close of the spectrograph. So in the middle here is the fisheye lens. That is filming the night sky, and it has a pretty big range. And then on the outside, all of these are the spectral gratings. So they're going to be able to find any meteors that come from any different directions. And if the box, the picture on the end here is where my project started. So if you're videoing surveillance of the night sky every single night, you have to store this data somewhere, and you need to analyze it. So here's the box of hard drives I was given of every single night from 2013, every single night till 2022, that have to be searched for the meteors so we can do a spectral analysis of them. And on some of these drives, this is what it looks like. So here's some meteor spectra. You can see I pointed out some oxygen lines and some sodium and magnesium lines that you can see straight away. Sometimes you just see the meteor, like down here on this panel, which is okay. You can still figure out a lot of information just if you don't get the full spectrum. But in addition to having the meteors in a night sky, you also have noise, such as airplanes will pass over, the moon, clouds, birds, anything can contaminate that. So you want to sort through. And so my job was to sort through. But that's very difficult to go frame by frame, clicking through a computer and sorting the meteors from the non-meteors and then doing a spectral analysis. So I automated this process. And my first step to automate it was I created a program to do basically everything for me. So no one else had to sit through and do this by hand. So we can have more time doing the spectral analysis. So I had a program where you plug in your hard drive into the computer, and it will take the data, the date of each night, puts it on the computer. It will then unzip each folder, because there's a lot of information on each folder and each drive, and then it will create spectral files folder, which is the stuff we want to look through, and then calibration files that come with each night. And then it will convert the data that comes in as bin files, and bin files are just video files, short little video files, so it will convert those into JPEGs, and I have to delete these unwanted files that comes out when I do this conversion. And then I separate everything into that one folder. I then send it into a classifier, so then it can do, this is a meteor, this is a non-meteor, and then it will put it in a false meteor folder or a spectral files folder. But I spent most of my time on this classifier part. To make an image classifier, I didn't know that you had to use machine learning. And most of you probably know what AI is. I knew what AI was, but I didn't know machine learning was a subset of AI. And with machine learning, you're still a human aspect of doing this feature extraction. So I wanted to completely eliminate that human aspect. I wanted the computer to do everything for me. So that requires deep learning, which is a subset of machine learning. Since I knew nothing of this, I, over one weekend, took a free code camp class on machine learning with Python just to help me a little bit so I can perform these tasks that needed to be done. So here is a basic example of an image classifier. I put the cat-dog example. I think it's the easiest to understand, and this GIF does a really nice job. So you're feeding the computer images of cats and images of dogs. And then these layers here, these like different little rectangles, are the artificial neural network. So you're making the computer have its own brain, basically. And you're training the computer to know the difference by feature extraction, to see the difference between a cat and a dog. And it will go by each image and pull out these features to distinguish the difference. And then it will pass it through this little small rectangle here, and that's the fully dense connected layer. And then it will bring everything together. All the neurons are connected at the end, and then they can spit out, is it a cat or is it a dog? So I wanted to do that. Sounds pretty simple. Absolutely was not. And so I wanted to do that with the meteor spectra and non-meteor. And as you can tell, some of them are really dim compared to what an airplane spectra might look like. So this was a very difficult job. It requires a large data set. So I created my classifier here. And here's my feature extraction layers I have. So I have 3 feature extraction, multiple hidden layers. So I have a convolutional layer. I added a rectified linear unit activator, and I used an atom optimizer. That was just the best one I can use. It just looks through the weights and produces the less loss rate. You want to have more accuracy. And then I added on a max pooling layer, and then I send it to the fully connected layer, connect all those neurons together, the computer's thinking of what it could be, and then it will spit out if it's a meteor or a non-meteor. So, like I said before, I have to convert these bin files to JPEGs because I couldn't figure out how to do a video classifier, but that can be done. So I did an image classifier. Then you have to create labels. So you have to tell the computer, I want meteors and I want non-meteors coming out of here. Then you send it your information. So I did have to build up a data set to feed the computer. A bunch of meteors and a bunch of non-meteors. And then you have to convert those images into numbers and then normalize them. Then you have to create the model that I showed on the previous slide, train the model on the data that you provided it. Then you have to evaluate, see what accuracy you're getting. This accuracy is basically a confidence, how confident the computer thinks its guess is. Then you just improve. An improvement involves making the data set bigger. The more information that you're feeding it, the better, the smarter the computer can be. So most of my time was spent right here in the creating, training, evaluating, and improving. So in the end, with my model, I trained on 996 meteors and 915 non-meteors. I had to build that data set up myself, so that's why it took a really long time. And I only got, well, I got a 93% accuracy, but if you look at the testing, I had 227 meteors, so new data that I'm feeding it to see how well it's doing on this, and 337 non-meteors, I only got an accuracy of 84%. So if your training accuracy is bigger than your testing accuracy, you're overfitting, which means the computer is now memorizing because your data set is so small, it's no longer learning, it wants to just memorize certain things. And you definitely do not want that. So to combat that problem would be a larger data set. But the day that I left my RAU, I ran it, the whole program, on one night just to see how everything was going. And it put 276 non-meteors in the false spectral folder, so yay. But then it put 3 meteors in that false spectral folder. So that was, and then in the meteor folder, it put 227 false spectral into the meteors. But it did get 14 meteors, so that cuts down the process significantly. But obviously, a small data set is considered 10,000 images. So having only 2,000 images was incredibly ambitious, and obviously it would need to be a lot bigger. But the point of this was to talk about the diversity of these comments. So once I was able to produce some comments from my tool that I created, my mentor and I made this plot. And this shows the speed on the x-axis and the sodium-magnesium abundance on the y. And that just tells you how much of one element versus the other element is inside these comments, in these meteors. And so our data that we got from my tool that we used is in the black dots. And the Slovakian group had a large data set that we can compare to, and they're the red crosses. So we just wanted to have something to compare our results with. The blue line that you can see up there is the normal cosmic abundance, and this is where you would expect to see certain meteor showers. But with ours, we found that Comet 73P was much slower, and as well, it had a significant amount of sodium magnesium. But if you move to the Geminids right here, they are considered sodium poor, and they move a lot faster. So just from these two meteors in this meteor shower to this comet, there's already diversity and so much you can see from different parts of the solar system. And if you move to the Perseids, they fall directly on the normal cosmic abundance is where we would expect them. But from 3 different groups, you can tell that comets also, they don't come from the same place, and they're also not made up of the same things. So my improvements on this project would obviously be building up a bigger data set that would just improve the accuracy, the confidence of the computer, and get that up to 95% would be ideal, and that would be the best results we would want. And future work would be, my mentor is writing a book about every single meteor shower and every single meteor within that shower and the spectral composition of each one. And so I am now a co-author on one of the sections in the book that has to deal with the tool that I created to automate this process. So I would like to thank my mentor and the NSF and all these other places that funded my REU for me to be able to do this research. So thank you.
All right, great talk, Clarissa. Who has questions about deep learning or other things involving comets? All right, with no other questions, we're going to move on. Thank you again, Clarissa. Next up is Mari Beltran. Mari went and worked on exoplanets this summer. And she went to the University of Kansas in, I think, their first year having an REU program. It was their first year.
Okay. Hello, yeah, I'm Mari Beltran, did my REU at the University of Kansas with my mentor, Dr. Ian Crossfield. So to begin, planets form by accreting or like building up material in the protoplanetary disks. It's proposed that the elemental abundances of materials in the star formation are the same as in this disk. Heavier stellar elemental abundances can predict the chemical composition of exoplanet atmospheres. When we're looking at exoplanet atmospheres, we want to look at their spectra. So a little example of like what the spectra is in the lower picture on the right. The sun, or the star, the light from the star is absorbed by molecules and elements in the atmosphere of the planet, and then creates a graph off of that. And different elements, different molecules are absorbed at different wavelengths of the star. So for my project, it was over the summer during when the James Webb Space Telescope was releasing its first batch of data. And more data that will be released will be exoplanets. In the top right-hand corner is one of the exoplanets that had the data released for the spectra. It is WASP 96, if I remember correctly. Okay, when we're modeling spectra, usually the assumption is that the elemental abundances for the composition of the exoplanet are similar to our sun. My project was to compare this the spectra using the solar elemental abundances to the exoplanet's host star's elemental abundances, which hasn't been done. And we want to see if there's a difference between the two, and if the difference would cause an impact on how planets are formed. The first thing I did was I had to come up with a list of exoplanets to model. My list is a cross-match between the James Webb targets that will be released and a catalog of stars that we have their elemental abundances for. So when matching those two, there were 28 stars, and on the top right-hand corner shows the carbon abundances comparison compared to our sun. So as you can see, there's ones with a lot less and a lot more than our sun. And then with these 28, I created thermal profiles. These are vertical temperature structures relating temperature and pressure together. If you think of an atmosphere, as you increase altitude, you decrease pressure, as you can see in the thermal profile of WASP 121b. Okay, cool. Okay, so with the thermal profiles and the stellar and solar elemental abundances, I was able to create chemical profiles. That's how much of a molecule is in the atmosphere at a certain altitude. The dotted lines are the solar elemental abundances, and the solid lines are the stellar elemental abundances. As you can see, there's a shift, so they are different. And then with these chemical profiles, I was able to create a spectra for each of them. Unfortunately, for the chemical profiling, the code only worked for the transiting exoplanets, not the directly imaged exoplanets. So in that case, I was only able to make 24 because there are 4 directly imaged exoplanets in my list. Okay. And so for the spectra, it's still the atmosphere of the exoplanet in the wavelengths, and the atmosphere is in terms of radii of Jupiter. In result, I was able to make 28 thermal profiles, 24 chemical profiles, and 24 transmission spectra. This is the chemical profile and transmission spectra of WASP-18b. As we can see, there's a difference in the chemical profile between the solar and stellar spectra, and we can see this correlated in the spectra. Because the solar and stellar abundances aren't matched up. And below is WASP 127b, where the lines are closer together. Therefore, in the spectra, the lines are closer together. This spectra shows a highlighted window in the H2O lines. And in the red box in the chemical profiles are the H2O abundances. And so because we can see the offset in the abundances in WASP-18, we see the offset in the spectra. Okay, so 12 of my 24 spectra did show the offset and showed a difference between using the 2 different elemental abundances. So the next step would be compare these spectra to the spectra produced by James Webb, and also to compare it to observations of these exoplanets. I would like to thank the NASA for funding my research and all the support I got from the University of Kansas and KU Exolab. Thank you.
You did great.
Are there any questions?
Megan, I'll bring the microphone over.
I was just curious, so for the transit radius, you're doing it in terms of Jupiter radii. Is that like the standard unit, or was that just the most convenient for your data?
So I was told to repeat the question. So the question was if using the radius of Jupiter in units for the spectra was universal. It was just the code I had that was used. Otherwise, I would have to do a lot of conversions to get it to match the atmosphere.
Thank you.
Any other questions for Megan today?
Go, Megan.
I'm sorry, Mari. Megan's right here. You can ask her questions this spring when she's giving her capstone talk. All right, I'm sorry, Mari. Next up today, we're going to switch gears, and we're not going to be up in the stars or comets anymore. We're going to go down to our ocean beds. And Amanda's going to tell us about things that she did on machine learning for the seabed parameter estimates.
Yep. Okay. So, like Dr. Richardson said, I'm Amanda. I went to the BYU University and worked with Dr. Tracy Nielsen on underwater acoustics. And when I first learned that I was doing machine learning, I had no idea what that meant. So hopefully I'll be able to help you guys understand a little bit as I learned as well. So the original motivation for all of this is that ocean acoustics is a very big field. It's used in a lot of different things, like finding oil deposits below the ocean floor, studying the habits of wildlife, and studying the impact that humans have on ocean wildlife. But there's also another aspect of ocean acoustics, and that is to map the ocean floor. As most of you know, the ocean floor is also a very unknown thing, just like space is. And with the recent technology boom that's happened, machine learning has been an incredibly crucial tool in doing all of this and learning more about the ocean floor. By creating machine learning models, we're able to run ocean spectrographs through it, and then hopefully the goal, the ideal, is that we'll be able to actually categorize and map a lot more of the ocean floor than we've ever been able to before. So one of the downsides to machine learning, though, is like Clarissa said, it requires a ton of data for it to ever be even hopefully accurate. And sadly, there is about 20 samples of ocean spectrographs that are actually labeled and are useful for what I was doing. So we had to get kind of creative and come up with ways to produce synthetic spectrograms so that we could still train our machine learning model. So what we did was a physics-based fluid model, as seen on the screen. So it starts off with this upper half space, which is the air, and then you have the water-air boundary, which is where a lot of sound reflections occur from passing ships. And then as you travel down the water column, you hit the water sediment boundary, which is where absorptions and transmissions and refractions occur. And all of these things, as you can see by the arrows, it kind of, the sound bounces around and then it eventually hits the hydrophone, which is our underwater microphone. Within all of this kind of distortion, there is unique sediment characteristics. Such, like, think of it when you sing in the shower in a bathroom with hard tile versus singing in like a living room. When you sing in a living room, it's kind of dampened. It's the same thing with the sediment. So sand bounces off, I guess, sound easier than hard, than like mud or gravel or stuff like that. So as ships pass overhead, all of that is picked up by the hydrophone. So here is an example of two different spectrograms. The one on the left is a real spectrogram, and the one on the right is a synthetic one produced by another REU participant. They look similar. They both have the same striations and U-shaped pattern. They should. If they don't, then something is wrong. But the difference between the two, the reason why they look different is because there are different sediment characteristics and ship speeds occurring. But the goal is that we take all of these synthetic spectrograms, plug it into our machine learning algorithm, and then it produces what we want to see. So we're going to take a quick sidestep for a moment, but it'll all tie in a second. So if you look at these numbers on the screen, you can easily, within a second, tell what all of them are, correct? Didn't even take you any, it wasn't even a challenge. If I were to tell a computer to do the exact same thing you just did with the exact same accuracy, it is significantly more difficult, just recognizing numbers, let alone seabed characteristics. So what we do is we create a convolutional neural network, like Clarissa was talking about, essentially creating a brain for your computer, where there's a bunch of hidden layers, and it goes through and it picks out different characteristics, and then it spits out what you want it to be. However, because of the data size that I was using, we couldn't just go with a normal convolutional neural network. We had to use something called a ResNet, which is a residual convolutional neural network, which takes information from these earlier hidden layers, saves it, and then as it goes down, it re-implements it so that you're not losing as much data as you're going through trying to learn, which makes it a little bit more accurate. So, sorry, hold on. My goal for the project was to classify, was to determine the sound speed and the density at the top of a sediment layer, and that was used using linear regression. So within my field of machine learning, there's two different types of machine learning. There's classification and there's regression. So think of classification like pass-fail classes. Either you passed the class or you didn't. There's no in-between. Whereas linear regression is more like a grading scale where, you know, there's percentages. The seabed is not, it's either a seabed or it isn't. There's a range, which is why I'm using linear regression instead. In terms of machine learning, there are two different categories that can be, two different parameters that can be adjusted. There's the parameters and the hyperparameters. Hyperparameters deal with changing the model itself, such as how much data it's taking in at a time, stuff like that, versus the parameters, which deal with what the model is trying to learn. Through various testing, I was able to refine both types of parameters prior to conducting my research. My research focused on looking at the sound speed and density at the top of the first sediment layer, both by themselves and then learning them together at the same time, with and without noise. Along with that, I focused on batch sizes of 256 and 512 with early stopping patiences of 3 and 4. The batch size is just how much data it's taking in at once, and early stopping patience is how long is it allowed to progress through its iterations without any improvement before it stops itself. Because then you run into issues of overfitting and stuff like that, which is not what you want. I also looked at two different ResNet models, the ResNet 18 and the ResNet 50. ResNet 18 has 18 hidden layers. ResNet 50 has 50 hidden layers. So, and because of that, I had to create 2 different sized spectrograms, one with larger data sizes to allow for more learning, deeper learning that the ResNet 50 would be doing. So while that was my goal for research, we realized about 2 weeks before the end of the internship that our script with noise was not hooked up to our main script for machine learning. So I was running tons of data thinking I was adding noise, and I wasn't. And we only found that out when we tried to look for patterns, and we couldn't see a single pattern between no noise and noise. We also realized that the hard drive, I guess, that we were using to run our machine learning models off of did not have enough internal memory to run the larger batch sizes for ResNet 50. So we don't actually know if ResNet 50 is a better option for this type of machine learning. So because of that, I will only be showing results where I intentionally did not run with noise, because that's the only reliable data that I was able to get. So here we can see the results, the sound speed results for the first sediment layer, for the top of the first sediment layer where the water and the sediment meet. So there, on all 4 of these images, there's a red line. That's kind of based off of literature what the expected value is. So the range is between 0.98 and 1.02. That's the accepted value. And as you can see, the batch size of 512 with a patience of 4 on case A had the best results. Case B is the smaller batch sizes. Case A are the ones, the larger spectrograms that I created. Again, this is the results for the top of the sediment layer for the density. And again, you kind of want, all of those dots are different ships, like different ships that we actually have physical data for. And we ran it through the machine to figure out how well it's actually able to guess. And again, you want all of the ships ideally to be within the red lines. And case A, once again, has better results than case B. And then this is when I tried to teach the ResNet model to learn sound speed and density at the same time. And both cases did kind of the same. Neither were super great. So now, what does all of this mean? It means, one, that the larger spectrogram sizes that I ended up creating for ResNet 50 were still useful. I was able to use them for my ResNet 18 and get far better results than what we were getting previously. Along with that, it didn't really seem like learning 2 parameters at once really made a difference, which was what we originally hypothesized would actually make it better, but it didn't. So that's kind of as far as my research went. And then in terms of progress, I know that Dr. Nielsen is currently working on adding the noise script to the main script so that we're actually be able to train with noise, because when you're taking real data, you have wind noise and ocean spray and all of this stuff that kind of adds noise to your spectrogram. So adding that into our synthetic ones will obviously help in accuracy. And then also adding in parameter uncertainty values into our machine learning, which is what I kind of touched on, but wasn't enough to put into my presentation at the end. Adding that uncertainty will help the machine learning model to actually learn better. So I would like to thank all of you for your time, and if there's any questions, I'd be more than willing to answer them now.
Any questions for Amanda today?
So on your graph, what did the patience number mean?
So what happens is within the data size, I think our data set was like 10,000 data points, and batch size is 512, which means that it's going to go through 4 iterations of picking 512 random data points before it's allowed to do that 4 times. And if there's not an improvement of, I believe it was 0.01%, it would stop running, because that means it was starting to overtrain, which means it was memorizing the data as opposed to learning the data. So that's just what that means. Increasing the batch size just is how many more iterations is it allowed to have.
Any other questions today? All right. Our ultimate last talk today, Janessa said she is going to knock our socks off.
Yeah, we're not in the ocean anymore. We're traveling to Washington, D.C. Yeah, mine got messed up. There's like a whole ordeal. How do I make this full screen? This? Okay. Got it. Boom. Yeah, so this is Janessa Puts On Her Socks. First, gonna thank Brad Conrad and Michaela Cleaver. They were my mentors. Who am I? I'm Janessa Sloan. I'm a senior here at Riddle, and I'm an active SPS member. SPS is the Society of Physics Students. If you didn't know, I was the SPS SOC intern this past summer. I'm an SPS AZC, which is Associate Zone Counselor, representing Arizona, New Mexico, and Mexico for 2 terms. And I have been our chapter's president for 2 terms. So I'm pretty much a walking SPS ad. So I'm going to talk about the SPS internship program just a little bit. So SPS is a national organization supporting physics and astronomy outreach, research, and a lot more. And you must be an SPS national member to apply. It's a small fee for a whole year membership. And it's a 10-week program in Washington, D.C. You're normally staying at George Washington University. And you're pretty much a 5-minute walk from the Lincoln Memorial, which is really cool. And there are about 12 different placements. I know they took a couple off and they're adding a couple on, but these include space telescopes, SOC, which was my placement, APS Outreach, AAPT, which is the American Association of Physics Teachers, Science Policy on Capitol Hill, working with congressmen, and NIST, which is National Institute of Science and Technology. And what's really cool is a stipend is included, and housing and travel also, and a bunch of fun events. I actually went to a Nationals ball game because it was really fun and paid for. And I actually met Dr. John Mather, had lunch with him, and also met Dr. Renee Horton, also had lunch with her, which is really cool. So like I said, I was the SOC intern. So this summer I basically worked on outreach. So that includes working on Astronomy on the Mall, which is a 50,000 person outreach event on the National Mall. I actually got to lead this, which was really cool, and I met Bill Nye the Science Guy. And I added to SPS National's demonstration library, which means I uploaded new demos of onto various platforms, just videos of me doing some new demos. And I worked on Physics and Astronomy Jeopardy. It used to be called Physics Jeopardy, but I changed that, and I am now calling it Physics and Astronomy Jeopardy, and this year it's astronomy focused. I also worked on my SOC, of course, which stands for Science Outreach Catalyst Kit, and it's intended to be used by chapters' outreach programs. So first up, I'm going to talk about Astronomy in the Mall. This is a photo of the interns at the mall, and you can see we were literally on the National Mall. The Capitol is right behind us, which is really cool. So a lot of things went into Astronomy in the Mall. I had no idea I was doing this until I think a couple weeks before. So a lot of planning, including researching what demos I wanted to take and purchasing all of those supplies and organizing and developing and testing all of those demos, and then organizing each of the volunteers for the demos, who were just the interns. And then I had all of the interns help me present. So we basically just think it's important to share our passion for science with future generations, which is why outreach is so important. So here is a photo of some of the interns at one of the tables, and these are all of the demos that we took. If you recognize one of the interns, Anthony Olgan, he was actually the Space Telescope's intern, and he used to go to Embry-Riddle as well. Next up is the demonstration library. So this is a photo of me performing Cloud in a Bottle, which is my favorite demo, and you can watch the video on SPS National website. So I added 7 new demos, including the electromagnet, Jolly Rancher bubbles, Cloud in a Bottle, fireworks in a glass, laminar flow, smoke cannon, and metal resonance. And all the videos are online. So here are some screenshots of all of the videos. My favorite one, definitely Cloud in a Bottle, but the best one is probably metal resonance. It took me the whole summer because I'm not good at circuits. So, so I was planning, this is actually an old screenshot, it's from August. I was planning on having each of the videos come out on the first Monday of every month, just so we can continue the engagement of chapters, so they could get excited for a new demo video. So all of them are already uploaded, and yeah, they're really cool. Please watch them, give them views, like, comment, subscribe. Next up is Physics and Astronomy Jeopardy. So this is actually a GIF, but it's a PDF because there was something wrong with my PowerPoint. But this is our chapter playing Physics and Astronomy Jeopardy last year, which is super cool. And I got to make it this year. So like I said, it's astronomy themed. We have all revamped questions, all focused on astronomy, and there are new categories, including alphabet soup, equations, planets and stars, relativity, of course, because I'm me, general, and miscellaneous. So actually, this wasn't shown. This is the answer. I actually had a prize for someone, but since it's a PDF, it's not going to work. But yeah, it's a G. Next up and last is my sock. So like I said, it's Science Outreach Catalyst Kit, and the picture to the left, is a design that I actually made, and they are going to use it from now on to tape all of the boxes for future sock projects, which is really cool. So the sock is basically a kit full of demos surrounded by one theme, and this year's theme is eclipses. So they actually let me have creative freedom on what I wanted the theme to be, but they did say that an astronomy theme would be nice. So I chose eclipses in preparation for the 2023 eclipse, and weeks 1 and 2 I basically brainstormed all of these ideas and figured out what demos I wanted to put in the box and how big the box was going to be, and what demos would fit and which ones would be the most efficient for younger students all the way to high school students. So then weeks 3 through 4 I built a plan for that, and I actually started ordering the materials and writing all of the instruction guides for the sock during weeks 5 through 6, and then weeks 7 through 9 I had to pack all of the boxes by myself, which was very fun and the best part of the internship. So unfortunately I don't have a sock with me today because the sock intern can't order her own sock. So I have all of the components of the sock listed and a photo. So the centerpiece is the wooden orbital model, and it's actually powered by a really small motor, and it basically just shows orbits of the Earth, Moon, and the Sun, intended for younger kids. We also have the Scale the Solar System demo, which comes with receipt paper and instruction guides on how to scale the solar system down to 1 meter, 2 meter, all the way up to I think 5 meters. And this is also intended for like elementary school kids, so they can visualize the solar system a lot better. We have our paper model demo, and that actually is also intended for younger kids, but it actually shows the solar and lunar eclipse. And then what's unique about this year's sock is the box is actually a demo as well. So I had cut here stickers ordered, and I placed them all on the boxes, and they're able to use a box cutter to cut them out and create their own pinhole viewer to safely view the eclipse. And then of course I included all the presentation guides just in case they needed them, and then the thumb drive with all the instruction guides. Thank you. Let me know if you have any questions.
Are there any questions for Janessa today?
So I have a question, and then I have a suggestion. So the question.
Got it.
So the sock can be ordered through the SPS website?
Yes.
Okay. And then the suggestion, you could still do the Jeopardy question, but just if anybody knows what I forget how to pronounce it. Yeah. I'm not going to.
Does anyone know what a syzygy is? We played this in SPS. No. I have a sticker to give away if you get it right. Yeah. He got it right.
You didn't answer in the form of a question.
I wish you could see it. I'm sorry that you can't see it, but. Yeah.
All right. I want to thank again all of our speakers today, and especially congratulations to Nicholas and Amara. I know Amara had to run off to class as they graduate with their astronomy degrees this semester. And thank you all for coming. We will have more Science Speaker Series events in the spring. Have a great day and good
Thank
luck on
you.
finals.